Okay, well, thank you for inviting me and giving me a chance to present. I'm apologetic about missing the last meeting. I had the wrong time on my calendar for some reason. But I'm happy to be doing it this today at the before the semester begins here next week. I'll be talking about really an overview of some of the projects we've been doing over the last many years on water injection and how rock mechanics plays a pretty important and central role in what we do in many of these projects. This is not a detailed talk on one specific topic, but you will get the flavor of why rock mechanics play such a big role in many of these projects. So here's an outline of the presentation. I'll be talking about first of all water injection in a case in the Gulf of Mexico, which is matrix injection, and then looking at impact of injection-induced fractures on injectivity and Prudhoe Bay. This is from many years ago, and then looking at what are the issues related to fracture containment and completion decisions and so forth. So it covers a pretty broad swath of territory, but I think you'll find that rock mechanics plays a pretty important role in many of these aspects of the problem. So there's one of the first platforms in the Gulf of Mexico was Bullwinkle, which is operated by Shell, and they actually decided that they were going to inject seawater into this very high permeability sand, about a 1 Darcy sand, which had gravel pack completions and essentially an ideal sand for water injection. They expected the water to go away without any difficulty. And so they took seawater from 150-foot subsea, deoxygenated it with gas stripping and chemical scavengers and bacteria control and calcium carbonate scale inhibition, and they filtered this all the way down to fairly small particle sizes, very good water quality, and so they expected this to be not a problem in terms of injection. So here's the particle size distribution of the water they were injecting. Very, very good water quality. All of this stuff worked out really well, except that when they started injecting, they found that the injectivity, the injection rate in the blue line declined very quickly. And in a matter of just a few months, their injectivity was down to a quarter of what it was when they started. Their target injection rate was about 10,000 barrels a day, but instead they started getting about 2,000 barrels a day. And to their surprise, they had to go back and acidize this well every so often. So for example, here's a HCl treatment, here's a mud acid treatment, and the injectivity went way up as they acidized with HCl and with mud acid. And this was for this particular injector, but they had 5 injectors like this, and every single injector behaved exactly the same way. And so the question was, well, why is it that you're getting such a large reduction in injectivity over time? The red line here shows the pump pressure. So they held the pump pressure below the frac gradient, so they were not fracking any of these wells. And there's many, many instances of this and this was at a time when it was absolutely prohibited. People would basically say, you never fracture your injection wells. Your water injection wells should never be fractured. That was the conventional wisdom at the time. And we had a joint industry project on this at UT at the time, which I had started back in 1990 or 91. And we did a very simple calculation. I said, okay, if you inject, let's say 10,000 barrels a day at 10 ppm, so that's 10 milligrams per liter, and you convert that into how much solids that is, it's about 16 kilograms of solids in a day that you're injecting, right? And that is about 5.8 tons in a year of solids. Now, you would think that these particles being very small would tend to go very deep into the reservoir and cause a relatively little damage. But actually, it turns out that these solids are trapped fairly close to the face of the wellbore, and in fact reduce the permeability dramatically over a course of just a few weeks. And so even if you filter the water down to 5 ppm or 10 ppm, which is very clean water, you tend to get a large amount of solids being injected into the ground when you're injecting large volumes. So large-scale water injection projects, you almost invariably inject large amounts of solids in the ground. By the way, the details of all this are published some time ago. So the injectivity basically drops off fairly quickly directly as a result of this. And the other thing you notice is that when you do hydrochloric acid treatments or mud acid treatments, you get a big increase in injectivity, which tells you that all of these solids that are accumulating very close to the wellbore. So this is all related to near wellbore plugging associated with the solids that are in the injection water. And they don't travel very deep at all. They travel maybe a few centimeters away from the wellbore. So this is the primary reason that you get this kind of injectivity loss. Now, while we were doing this project, we were also involved in Prudhoe Bay, which was at that time injecting about 1.4 million barrels a day and 0.9 million barrels a day of seawater. So produced water and seawater were being injected. We have about 197 injectors. This is still going on. This is there are about 200 injectors right now, and the volumes are a little bit larger than this. And in this particular case, they had built a very large facility in the North Slope, BP had, and there was no decline in injectivity observed, injecting 2,000 ppm of solids and oil into the ground. And of course, they were injecting under fracturing conditions. And so without knowing it to begin with. In fact, they started off with a very expensive water treatment facility, about $500 million to actually build the facility and then treat the water and then inject very clean water. And what they realized was if they bypassed the facility completely, nothing happened. The injectivity remained basically constant. So they began to then treat the water less and less. And what they realized was that if you inject produced water at 150 degrees Fahrenheit, you get a frac gradient of about 0.57 to 0.6. Seawater injection, which is cooler, you get a frac gradient of about 0.53 to 0.54. And of course, the orientation of the wells also affected the injectivity. So this is a paper from BP looking at the wellhead injection pressure versus the injection rate. So let's say you're injecting 10,000 barrels a day of seawater or produced water. The open points here are seawater, and the red line and the dark points here are produced water injection. You can see that the difference between these two pressures is almost 500 psi. 1,000 psi versus 1,500 psi of surface pressure. And so you get a huge difference in injection pressures, primarily related to the temperature of these two fluids. So this is entirely related to the thermoelastic stresses that are created as a result of injecting cold seawater as opposed to warmer produced water. So clearly, under fracturing conditions, when you have injection-induced fractures, you tend to get a significant change in the injection pressures associated with thermal stresses that you can get. So this is, at this point, we had we were having discussions every 6 months with our GIP members, and this was something that came up as being an important consequence of fracturing these injectors. They also noted that I'm not going to go into the details here, but the deviation and the azimuth of the wells played an important role in controlling what the injection pressures were. Once this was all discovered, once this was all it came to the forefront, fracturing in injection wells became a really important issue, and exactly how this fracturing occurred was an important consideration. So people began, in fact, people would thump on the desk in our meetings and say, we never fractured our injectors because fracturing injectors is bad, and so we never fractured our injection wells. And I would basically tell them, I said, go back, test your injection wells, and I can bet you that almost all of them are fractured. And in fact, I would say that today, probably over 95% of all injection wells are fractured, either intentionally or unintentionally. And so there's most of these fields that you see in the North Sea, Forties field and so on, there's very large volumes of water being injected and have been injected for decades. East Texas is a good example. West Texas is a good example. literally hundreds of millions of barrels of water being injected. I will say that produced water is one of the largest man-made quote unquote waste streams that we generate. It's a very, very large volume of water that we inject every day, produced water as well as seawater and other sources of water, right? So it's a huge number of injection wells in the world. So if you do matrix injection, you get very, very short half-lives. In other words, the injectivity drops very quickly. What you see in practice is that removal of fine filters has no adverse effects on injectivity of seawater. An injection of 50 to 1200 ppm of oil, 5 to 50 ppm of solids, basically the injectivity drops to some value and then remains constant. And same thing with all these fields in the Norwegian sector. This is a field in South America where we had done a study on looking at in a high stress environment, the injection rates drop off very quickly. So the injectivities drop very, very fast. The injectivities are dropped by an order of magnitude or more. Whereas if you do in the same field, if you do in low stress environment, the injection rates remain relatively constant and the injectivities remain relatively constant. Again, fracturing conditions versus non-fracturing conditions. So in the last 35 years, we've done probably 40 different field studies around the world. These are some of the fields we've done in the Gulf of Mexico, offshore Africa, and so on, where we've done water injection studies and looked at fracture growth and so forth in all of these cases. So to prove that this is actually happening, because in most of these field experiments, if you like, of I wouldn't say experiments, they're field injections programs, you find that there is no obvious indicator that you have fractured these injection wells. There's no red flag that pops out and says, I'm now fractured. You just happen to keep injecting and the water keeps disappearing in the ground. And as a matter of course, you don't realize that the injection well is indeed fractured. But you can actually show that this is happening in a very controlled experiment. So we did these large block tests. These were done at TerraTech, in fact, back in the bad old days. And here's an injection well with perforations down here. And the stress is applied. So there's 2000 PSI here, 1450 PSI here. And when we ran these tests, we had requested multiple pressure ports to measure the pressure along the azimuth of the fracture. And as you inject this fluid, which contains different types of particles for plugging, you can see the fracture growing by monitoring the pressure at these locations. So here's a typical experimental result that we did several of these block tests. Here's the injectivity as a function of injection time over 24 hours. The colors in the background indicate different types of fluids that were being injected. So these were oil and water emulsions, more concentrated emulsions, different types of polymer, latex particles, and so forth. What you realize is that the blue line, which is the injectivity, is constant no matter what you're injecting. So essentially, the injectivity remains constant regardless of what kind of particles are being injected, what kind of plugging you're getting, and so forth. And every time you inject brine, which is this white bar that you see in the middle, every time you inject clean brine, you find that the injectivity rises. So you find the injectivity rises. And every time you see that consistently, you see that every time you inject brine, the injectivity rises. And of course, what's happening here is every time you inject particles, they cause plugging, and the plugging causes the fracture to grow. And when you stop injecting the solids, the plugging stops. And then when you inject brine, the fracture continues to grow, and that causes the injectivity to rise, right? So this is seen very, very consistently in all these experiments. The growth of the fracture can be monitored. So this is two wings of the fracture, one going in one direction, the other going in the other direction. And depending on what you're injecting, what kind of particles you're injecting, the rate at which the fracture grows changes. So here, for example, this particular type of particle, the fracture didn't grow very much at all because it wasn't very effective at causing plugging in the rock. So the effectiveness of the particles at plugging the face of the fracture controls the rate at which the fracture grows. So here, for example, the fracture doesn't grow very much at all. Here, the fracture grows very fast because these particular type of particles are extremely effective at plugging the face of the fracture, and that causes these fractures to grow extremely quickly. So the nature of the plugging controls the rate at which the fracture grows, right? So particles in the water do control how fast the fracture grows, how long the fracture grows in these injectors. And so we also took cores in this particular case. They were these orange particles that had been injected. We took thin sections of these and we looked at the tip of the fracture to see how the fracture was actually propagating and where the particles were being plugged. And what you see is that the particles actually are trapped within the first few millimeters of the face of the fracture. So this is the face of the fracture here that's propagating in the rock. These are the particles that are plugging the face of the fracture, right? And most of the particles that we see end up very close to the face of the fracture. So they don't travel very far into the rock. So this is a cross section of the whole experiment. And at the end of the experiment, we had actually injected some different colors of particles. These are black particles that we injected. And so you see that most of the particles at the end of the experiment end up at the tip of the fracture. So the injected particles are not plugging this part because this is already plugged. What it's plugging is the part of the fracture that is unplugged. And so you end up seeing all these particles ending up near the tip of this fracture. So that was a convincing evidence that, in fact, the particles are causing plugging near the tip of the fracture. So the lessons learned were the injectivity remains constant despite plugging by the particles. And this wellbore pressure drops abruptly when brine is injected. And the rate of fracture growth is closely related to particle trapping. And of course, to the geomechanics that results as a result of all the changes in pore pressure and so on. There were no thermal effects here, so you don't see any thermal effects, but this is all related to particle trapping. The invasion depth of these particles from the fracture face is very shallow, with a few centimeters at the most. And there is some evidence of fracture filling when you have high concentrations of oil and solids. This, by the way, is an important factor that if I get a chance, I'll talk about. And these injected particles end up mostly at the fracture tip, except when fracture filling occurs, right? So why does this matter, and why do we care so much about this? Well, the reason it matters is that your ability to dispose of water in very large volumes and to do a water flood or to do a disposal project depends entirely on your ability to propagate these fractures and on the rock mechanics associated with the growth of these fractures, right? So the growth of these fractures occurs directly as a result of this plugging that happens. And this plugging is directly coupled with the growth of these fractures because this external filter cake that forms offers a flow resistance which increases the pressure in the fracture, reduces the leak off, and essentially it's a fluid leak off control material in hydraulic fracturing terms, right? And this is an extremely important effect in large scale water injection projects. Of course, the other effects that are important are thermal effects and pore pressure effects. So injection of cold water clearly reduces the fracture gradient. This has been measured in the field. You can also measure this in the lab, and many studies have been done on showing the effect of thermoelastic and photoelastic effects, right? So this is something that you can do analytically that was done by Perkins and Arco back in the 70s or in the 60s. And you can see that there's a change in stress associated with temperature and with pore pressure. You can do this analytically. You can also do it numerically, which is what we do today. So the growth of an injection well fracture basically is the bottom hole pressure starts here. It increases because of plugging. As you exceed the sigma H min, you basically create a fracture, and then the injectivity and the bottom hole pressure remains relatively constant, right? And so the injectivity will remain constant. And this is the area when this is the time when the fracture is growing steadily over time. So the consequences are you save a tremendous amount of money in injection in the treatment of the water, but on the other hand, there's consequences downhole in terms of the length of the fractures that you get. So if you have 30 ppm, you may get longer fractures. If you have 3 ppm, you'll get shorter fractures, right? So in all these cases, these effects, these photoelastic effects, thermoelastic effects, and injectivity decline due to particle plugging all play an important role, together with the usual suspects, things like relative permeability and viscosity and so on. So these are all coupled together, and you tend to get fairly complex behavior over time in these injection wells. So to model all this, we have actually, in the last 10 years, we've built, the last 15 years, we've actually built the simulator to model not just this process, but also hydraulic fracturing, but certainly the capture the flow and the geomechanics. So we have, this model is modular in the sense that it has a reservoir domain, it has a fracture domain, and it has a wellbore domain. And in the reservoir domain, we solve what I would call a compositional reservoir simulator. So this is it can be black oil, it can be single phase, or it can be a compositional simulator. And then we also solve the displacement equations, or the solid deformation equations, which are coupled through photoelasticity with this. We solve the temperature equation or the energy balance, either using an enthalpy formulation or using a temperature formulation to include thermoelasticity. I have a PhD student right now working on adding a geochemical model, which allows for reactions, equilibrium or kinetic, for minerals dissolving or precipitating and so forth. So this is something that we've just recently added. And then there's a fracture domain, which of course couples directly with, as a boundary condition, to the reservoir domain, which solves the pressure equation, the component balances, so you can do mixtures of gases or liquids as a fracturing fluid. It does particle plugging, proppant transport, things like that. Looking at proppant transport, this is extremely important in many of the applications we've dealt with recently. The fracture temperature equation, so the temperature changes along the fracture. And recently, in the last 3 or 4 years, we've added natural fractures using a displacement discontinuity model. And so if you have a DFN, you can actually propagate a fracture within the DFN to see what happens with the propagation, the interaction between the hydraulic fracture and these natural fractures. All of this applies to water injection and to a whole bunch of other problems, of course. And then finally, we have the wellbore domain, which when I started this process 15, 20 years ago, I felt would be probably the least important, but it turns out to be one of the most important. So you do solve the component balances, the pressure, the temperature in the wellbore. And most importantly, we have the ability to simulate proppant transport within the wellbore and distribute that proppant in some fashion along the wellbore into different perforation clusters. And it turns out that the proppant doesn't always follow the fluid. In fact, it never does. So you get a different distribution of proppant along a horizontal wellbore than you do fluid. And that turns out to be extremely important in terms of designing completions and designing fracturing treatments and coming up with optimum cluster spacing and optimum cluster design and so forth. So this is a very important part of the overall model. And this model then decides how much proppant goes into each fracture and goes into each cluster and so forth. More recently, we've actually done a model for a water injection well, horizontal water injection wells with inflow control devices. And I'll talk very briefly about that, since the topic here is indeed a water injection. So I'll very briefly show you the equations that we solve without getting into detail, obviously. So we solve essentially the displacement equation, we solve the flow equations, the pressure and the saturation equations for black oil. If it's a compositional model, we solve the component balances. And then this is the temperature formulation for the energy balance. So those are the equations we typically solve. Without going into any details, I want to show you some very simple examples of the results of some of these models. The details of the theory and so on are in the papers, which you'll see the list of those in the end. Keep in mind that the water injection fractures, the geomechanics is happening over decades, right? This is almost 20 years of injection. And these fractures are then growing over time slowly, and exactly what happens to them and so on. One of the interesting problems we dealt with recently in the last 4 or 5 years has been what happens if you have fractures growing in a sand that is overlain by shale. And one of the key questions was containment. So this is a water flood in which seawater is being injected. This is a field in the Bering Sea where fractures are growing. And the question is, will this fracture be contained within this particular sand? And the usual way of doing that is to say, okay, you have a stress profile and the containment is controlled by that. The question that came up here, which was unusual, was how big a role does thermal conduction play in the containment of this fracture? In other words, I'm cooling down this portion of the rock, and when you cool this down, what is going to happen to the stresses in the shale above because of conduction? And it turns out that most people neglect conduction when you have cold water injection, but you can actually get significant changes in the shale stresses overlaying the fracture. And this change in these stresses, because of thermoelastic effects, can play an extremely important role in containment issues associated with this. In this particular case, the field was sold because of the danger of the fractures not being contained. And there was no water injection initiated in this field as a result of this non-containment. And this is an important example of how thermoelastic stresses, photoelastic stresses, together with the stress profile and the rock mechanics of the rock itself, plays an extremely important role over long-term injection. The one big difference that you see here in these cases of water injection as opposed to hydraulic fracturing is you're injecting extremely large volumes of water. And so the temperature changes that you get are much more significant than you do in hydraulic fracturing. In hydraulic fracturing, you may inject for a few hours, maybe a couple of days in long horizontal wells. Here, you're injecting over years. And so the volumes of water that you inject and the cooling that you get is much more significant than you do get in hydraulic fracturing. So you can really get a tremendous amount of change in stresses as a result of these things. I'll give you another example of what happens when you have water injection into a frac-packed well. Many of the fields in the Gulf of Mexico with their unconsolidated or poorly consolidated sands have frac packs associated with them. The question then becomes, how do these frac packs respond to long-term water injection? And we've done about a dozen studies on looking at this problem. And essentially what happens is the frac pack actually grows with time. And so over time, you can see an increase in the width of this thing. And so what happens to the frac pack? Well, the sand or the gravel that's in the frac pack actually slumps down, and you lose sand control as a result of this. In other words, in the beginning, the frac pack is fully full of proppant, but then when you widen it, the sand actually settles down and you lose sand control. And as a result of that, you can actually get some significant fill up of the wellbore with sand. And this is something we've observed many, many times. And the ability to model that is actually really important. As a consequence of this, where you place the perforations in the sand is quite important. So you place the perforations here, place the perforations there, or you place the perforations there. This can make the difference of a fairly significant commercial decision in terms of you tend to get much less sand control in this scenario because the sand is already slumped at the bottom, and as a result of this widening of the fracture, you tend to get loss of sand control in many of these completions in the Gulf of Mexico. So geomechanics has a direct impact on how you complete the well and ensure efficient and effective sand control over long-term injection of water in these wells. Another case study we've just finished last year in the Middle East was on inflow control devices. So these are inflow control devices which allow water to be channeled into different sections of a horizontal injector as a direct result of placing these packers in place and adjusting the delta P in these inflow control devices. 20, 30 years ago, it was rare to find inflow control devices in wells. Today, they're used more and more, right? And so you can actually see how the fractures grow in these situations, in these complex situations with wells that have a lot of jewelry in the well. And this particular example, they actually had 13 inflow control devices in the wellbore. And the question becomes, how many do you use? Where do you place them? How do the fractures actually grow in these? All geomechanics related. It's all completely geomechanics related, right? And what impact does this have on the distribution of flow along the horizontal wellbore, right? So with the ICDs, whether you have 2 ICDs or 3 or 4 or 5 ICDs, makes a big difference as to exactly how long the fractures are and where the water, how the water is distributed within these things. So ultimately, the growth of these injection-induced fractures can have a significant impact on oil recovery and reservoir sweep, right? And so if you imagine a cartoon like this, where you have an injection well and production wells, and the fracture is growing here, you can actually get clearly bypassing of some oil as a result of this poor vertical conformance or poor aerial conformance as a result of this injection, right? And some years ago, we had done some work on looking at what happens if the fracture grows like this towards the producers versus away from the producers. And you tend to get a fairly large change in the oil recovery, 10, 20, 30% change in injectivity. And I'll show you one example of this, of an extreme case of this, which actually is not that extreme, but this happens all the time. So let's say you have 2 layers, 2 sands, and 1 shale in the middle. And the fracture is growing in only one of the sands. Well, if you look at the oil recovery in this scenario, guess what happens? Almost all the injection water goes into the fractured sand, and hardly any of it goes here. As a consequence, the oil recovery is much lower in the fractured case compared to the unfractured case. And that is a factor of 2 change in the oil recovery, directly as a consequence of fractures growing in some layers and not growing in others, right? And this is purely a result of fractures growing and the flow allocation between the layers being completely switched around. In other words, you're now getting 95% of the water going into the fractured layer and less than 5% of it going into the unfractured layer. And so you get early water breakthrough. You get very early water breakthrough. The water cut starts to increase very quickly. You get very poor oil recovery, and you get this thief zone that takes all the water. Now, thief zones historically have been associated with high permeability zones. Today, when we think about thief zones, we don't think about high permeability zones. We think about low stress zones, because low stress zones are the ones that are going to cause these fractures to propagate. And that's where all the water is going to end up, unless you use ICDs. So if you use an inflow control device, you can prevent this from happening. And that's what most people are doing today as a result of realizing that they have fractures. 20 years ago, most companies would ignore the growth of these fractures in these injection wells. Today, I think most people are well aware that this is an important and extremely significant part of their design of a water flood or a disposal zone. Right? So this is extremely important. This, by the way, is also very important in horizontal wells. So this is a field study offshore Canada, where there was a producer in the oil leg and an injector in the water leg, and this is the oil-water contact. And when they first came to us, they basically asked us, how clean should the water be? How should we treat the water so that we don't, so that we can inject over long periods of time? And when we did all the modeling and so on for them, and showed them that there's a good possibility of fractures being created, injection-induced fractures being created. What is the orientation of your well bores relative to the sigma H min and sigma H max? And they said, we don't know. We said, well, that's extremely important, because if you have wells that are oriented this way and the fracture is growing in this direction, well, that's bad news, because you're actually going to get something like this happening. The water flood front is going to break through much quicker than you want it to, and you'll bypass all this oil. This is all bypassed oil. So as a result of this study, I think they changed the orientation of their injection wells. So the drilling program was changed. What started off as a question about facilities and water treatment turned out to be really changing completely the way that the wells were oriented and drilled. I will say one other thing on these stresses, and that is the original stresses that you have in the reservoir are, of course, controlled by the in situ stresses that you've had over geologic time. But as you start injecting, so here's an example, a very simple example of an injector and a producer. And the lines that you see here are lines of sigma H max. And so you can reorient your stresses as a direct result of injection and production. And this is photoelastic effects only. These are thermoelastic effects, and these will change your stresses around the injector and the producer, not just the magnitude, but also the orientation. And this can be quite significant, actually. In many of the waterflood programs that we've studied, you can actually get significant changes in the stress directions as a result of injection of cold water at high pressures. So photoelastic effects and thermoelastic effects can change the orientation and magnitude of both of these things, and injectors and producers. And of course, this is just a very simple example of one injector and one producer. You can get much more complicated cases of this as you go forward with multiple injectors, multiple producers, and you can see line spot patterns, line drive patterns, and how the stresses are changing. So geomechanics and fluid flow are very closely coupled. In these particular examples, there's no growth of fractures in the injectors. If you start growing fractures in these injectors, I can show you more examples where the stresses are changing as a result of injection and production from these things. And of course, real reservoirs don't have these very nice patterns. They have much more complicated injection and production well patterns. And so you can actually get regions of stress reorientation and even complete stress reversal seen throughout the reservoir and not just limited to the near wellbore region. So we've done some examples of that over the course of some time, and you can actually see as the displacement occurs, the stresses are reorienting, and you can actually get some very interesting patterns that can develop. And if the geology is more complicated, all these are actual cases. This is an actual case of a channel sand where there were injectors and producers within these channels, and then the geomechanics becomes even more involved, because now you have a combination of these sands and more and less permeable rock that surrounds it, and the geomechanics of that can get complicated. So I don't have time to get into all these details, but we've done some history matching and details of injectors and producers and how do you orient them, where do you locate them, and so forth. The last topic I want to cover, since I'm running out of time, I have about 5 minutes left, so I leave time for questions. Is the project we've been involved in the last couple of years through the Bureau here on looking at water injection and disposal in the Permian. Many of you are aware that a huge amount of water is being injected into the Permian right now. This is the cumulative, DMG saltwater disposal in billions of barrels. So this is about 8 billion barrels. And so it's just incredible how much volume of water is being injected into the Bell Canyon. These are all Cherry Canyon, Brushy Creek. These are all zones within this particular area of West Texas and New Mexico. The big issue here is induced seismicity. And Peter Hennings and Katie and Smythe are the folks at BEG doing a lot of the structural modeling, structural geology here. But what they've found and what the program is found is they've mapped this change in surface elevation using satellite imagery, using TextNet, and so this is something that they've mapped. And so you can see here, for example, 7 to 12 centimeter uplift versus -11 to -17 downlift. So it's actually significant changes in the ground profile in these cases. And so what we're doing now is beginning to model some of these cases where since we calculate the displacements and the stresses and the fracture growth and so on, in these naturally fractured rocks, highly naturally fractured rocks, we have a DFN, we can propagate a fracture, We can see how the pore pressure evolves, and why is it that you get induced seismicity in certain areas that are far removed from where the injection is happening, right? So the injection may be happening in one location, but the induced seismicity may be happening 10 kilometers away. And the question then is, why is that happening? What is the nature of that, and so on. So we're just beginning to understand this interesting problem of how exactly these pressures propagate or the stresses propagate in these, and trying to understand using the geology and the structural the faults in both in the deep and the shallow zones where things are going. So just to summarize, there's very interesting questions related to water injection in terms of fracture growth, long-term fracture growth over decades, and what kind of this has implications in water quality specifications, facilities, and injectivity over time. So just production water treatment facilities, injection facility specifications, wellbore flow. These are all impacted by geomechanics directly, right? Where is the water going? What kind of fracture growth do you have? The distribution into multiple layers. What is the recovery factors? What is the containment issues in these? Those are all really important issues. And then, of course, look, it has implications in what type of completions: open hole, cased hole frac pack, cased hole gravel pack. Do we use ICDs? How do you design the ICDs, inflow control devices, and so on? So it also has, I didn't talk about this, but also has implications in drill-in fluids and perforation strategies. How do you place your perforations in vertical wells and horizontal wells, and so on? So just to sort of quickly summarize what I've already said, most sands will sustain injectivities for long periods of time if injection is above the fracture gradient. Now, obviously, you can't inject above the fracture gradient for the bounding shale. You can only inject above the fracture gradient for the sand that you're injecting into. That's just by the permitting that requirements that you'll have, right? So injection pumps can be designed accordingly. Otherwise, if you don't inject above the frac gradient of the sand, then matrix injection will lead to formation plugging and very quick declines in injectivity. This is almost universally true. There's very, very few exceptions to this. Poor water quality does not affect long-term injectivity. This is very counterintuitive for a lot of people, but poor water quality will not affect long-term injectivity because it just creates longer fractures. And this can have a significant impact on reservoir development plans and oil recovery, right? So really, you have to be aware of the fact that if you inject poor water, you're going to have consequences downhole in terms of longer fractures, even though you're putting the water away without too much difficulty. And thermal stresses, poroelastic stresses can play a very important role in controlling injectivity containment and oil recovery. So as I gave you an example of a gravel pack completion, sand control may be compromised if one operates above the frac gradient. And so you have to be careful about how you do that. In terms of oil recovery and so forth, good vertical and aerial sweep must be maintained in these injection programs. Cross-flow between layers can be a major factor causing loss of injectivity. I didn't talk about this, but water hammer effects should be avoided. And this can, we've had several studies looking at sand fluidization and wellbore fill-up. Periodic monitoring of the injection profile is good operating practice, but is rarely done in multi-layered reservoirs. In a couple of cases where this was done, the injection profile did change substantially over time because of the growth of these fractures. And so I think I've said that. There's a bunch of references here that you can go to. I haven't updated this since 22, I suppose, but there's about several papers in the last couple of years as well. So containment issues that I talked about is in a field case, role of heat conduction and so on. How do you couple fluid flow and some of the geomechanics in some of these things, proper settling and embedment, and so on. So there's things on looking at stress reorientation in water flooded reservoirs. These are all studies that were done and on looking at the modeling of this aspect, and then some older papers related to water injection wells and some case studies and some modeling work and so on. So there's a fair number of references that you can go to for more details on some of the examples I've shown you. So I will stop there and thank you for your time. And I've gone, I think, maybe a minute over, but I'll stop there and take questions.
All right, thank you so much. Thank you so much, Mukul. So that was excellent presentation and great to learn about, about fracturing and the role of geomechanics for conventional operations. So you have quite a few questions. So let me go through the chat and read those. So the first one is actually, it's a question from William Harbert. He asked about the, this large block experiments. What's the size of the block?
It's about 1 meter cube.
About 1 meter cube. All right. Okay, that's good. So the second question from Santiago Siribrinsky. So he's wonder what's roughly the particle size versus pore size, or do you have like a microfracture? So essentially, how do particles go into the rock? Is it just through the pores, through micro cracks, and what's kind of the size of all these features?
Yeah, I think you can actually get both happening. Depends on the rock, of course. You can definitely form micro cracks, but either case, no matter whether it's micro cracks or whether it's pores, the particles are unable to travel very far into the matrix. You're basically plating these particles out very close to the face of the main fracture.
Mm-hmm. And so yeah. These pores are pretty large, right? Because I mean, because we often think in terms of unconventional, so nanoscale pores, but these are pretty large pores, right?
Yes, these pores are huge compared to unconventional. So these are 10 to 20, 30 micron pores, and the particles are 1 to 2 to 3 microns. So they're about 10 times smaller than the pore size. But we've done a lot of experimental work as well in the lab. And despite the fact that the particles are much smaller than the pores, they tend to get trapped very quickly within a few centimeters. And essentially, the rock acts as an excellent filter.
Awesome.
It's really an excellent filter.
Okay, so thank you. So the next question is from Susmito Naha. I hope I pronounced it right. Is there anything different in these outflow control devices versus conventional ICDs?
There's a huge amount of variety in these ICDs in terms of what you can do with them. Some of them are mechanically operated, some of them are hydraulically operated, some of them you can actually do real-time control, which is rare, but you can actually, in principle, do that. So there's a lot of variety in this, and I think that the choice of what you use depends very much on your specific application. So there's a large variety of applications.
All right. So the next we have a few from Dana Jurek. So I mean, first of all, he says that this long-term time aspect is so very critical, which we which we obviously agree upon. So his question is why ICDs are not used in unconventional hydraulic fracturing reservoirs?
Well, generally the ICDs are used for long-term injection. So most of the unconventional is essentially using plugs for isolating stages in a frac, of course, and of course Dana is very well aware of unconventional applications, but it's a very different application. It's a very different application in these conventional reservoirs with long-term injection. And ICDs allow you to then, over the long 20 years of injection, control how much water is going into each of these different things. Now, it may be possible to use them in unconventionals during hydraulic fracturing, but it would be a much more expensive operation, much more expensive. And Dana, we would like to use some of your fiber as well in these water injection projects long-term, not behind casing, but maybe in well.
All right. So the next question from Marek Jarosinski. And so in a nutshell, his question is about natural fractures. So what would be the effect of natural fractures in the model? I guess it's for water flooding operations.
That is an excellent question, and I guess I cannot give you a definitive answer except to say that they play an extremely important role. We know this from the work we've done both in water flooding and also in in some of the geothermal work that we've been doing. But you can actually get almost invariably in water flood operations, you're surprised by where tracers and where water shows up. You're injecting over here and you expect it to show up in the next well, and it shows up 3 wells away. And so clearly natural fractures are playing an important role, which is why structural geology and understanding the natural fracture system is so critical in all these applications, particularly in wells or in formations that are tend to be more naturally fractured. You can get a huge impact of these natural fractures. And so I think my simple answer is we know they play an extremely important role. We are not able to adequately handle them because we don't understand them enough in the subsurface. Mathematically, we can handle them, but we just don't have a good description of them right now in many locations. And that's what we're trying to do in West Texas in these induced seismicity cases that we're looking at.
Excellent. So I have another one from Dana. So how about the modeling or like similar modeling? Has this been applied to CCS injection projects?
Yes, one of my PhD students right now is actually applying this to a CCS project, the geochemistry part, because when you inject CO2, you actually get reactions of the carbonic acid with the minerals, and we're applying this model to CCS projects right now. There's been 2 papers we've published in the last year on that, because there we are trying to look at how the CO2 reacts with the brine and the minerals and what kind of minerals can form. And what is the chemistry of the in situ brine, the mineralogy of the rock plays an extremely important role in controlling these geochemical interactions. So yes, we can apply these models now that we have the geochemistry, we can apply it for CCS.
Excellent, excellent. So we have 2 more questions. So the next one from Leopoldo Sierra. So he wonders whether the induced fracture actually significantly affects hydrocarbon recovery or production.
Well, it depends. It depends. If you have a homogeneous reservoir, the answer is no. But reservoirs are hardly ever homogeneous. And so if you have layers and if you have heterogeneity, then the answer is absolutely yes. You can have the hydraulic fractures that you create during injection can play an extremely important role because, as I showed one simple example, it can create thief zones when you have multiple layers that you're injecting into, right? So it depends on the geology.
Excellent, excellent. All right, so next one from Ed Siebrits. So it's about water injection in the Permian. So he says there's surface elevation changes in the Permian, right? And so his question is this mostly due to activated faults, or it's the result of the kind of sort of swelling due to fluid injection?
So a good part of this surface elevation and depression that's being seen has been seen the largest ones have been seen in areas where you've begun to have shallow injection. So if you remember some years ago, 3 years ago, deep injection resulted in some a slip of basement faults. And so the Railroad Commission approved the injection of shallower injection. By shallower, I mean a few thousand feet injection zones. And in those areas, you see more of this surface elevation or depression as a result of this shallow injection. So I think it's mostly related to buildup of pore pressure and then the displacement of these zones up or down, depending on where the fluid is going. But it's a very interesting and extremely important problem because without disposal of water, you cannot produce the oil. And so you basically shut down operations if you cannot get rid of the water. And so getting rid of the water is extremely important. And you want to inject the water without any consequences to the surface. No induced seismicity or induced seismicity events below 2, for example, is the usual goal. And then hopefully no big changes in surface elevation. That's the goal. And and in the extreme case, no surface expression of fluids, which has happened in a couple of cases.
Mm-hmm. And actually, we get just one more question. So it's probably going to be the last one. And so it's about also induced seismicity. And so it's from, well, there is no name, like Z. Philip, I guess. Philip. So induced seismicity is typically observed reasonably close to injections due to leak-off and shear slippages. So what do you think are the reasons for induced seismicity located like a few kilometers away from the injection? That's what you observed in the Berman.
Yeah, that is a good question, and we don't know. We don't know why induced seismicity occurs 5 or 10 kilometers away from where the injection is happening. But the evidence, just based on this huge number of seismometers that we have installed over the last 10 years, we know where the induced seismicity is occurring, and we know where the injection is occurring, and they don't always correspond. In fact, in most cases, you see induced seismicity occurring relatively far away from where the injection is happening. And the question is, why is that happening? And we don't really quite understand that. We're still working on we have different hypotheses of why that may be happening, but we don't really know.
Excellent. Thank you. So these are all the questions. So thank you so much again for your presentation.
Well, thank you all for your time, and thank you for listening. And we appreciate ARMA and they're organizing these events. So thank you for that.